In this review, we'll cover a few calculus techniques that will be helpful for us in solving derivatives and integrals of various problems that present themselves over the course of our 2 semesters of physical chemistry. Specifically, we'll look at the chain rule, the product rule for taking derivatives, and then U substitution for integrals. And I'll mention integration by parts at the end, but it won't be a focus of the course or the review. So let's start off with the chain rule. So the chain rule is going to be useful when you're trying to take the derivative of a function, and inside of that function is another function. That's not simply x that we're trying to take the derivative with respect to. So we can write out a formalism for this. So if we're taking the derivative of some function with respect to x, but rather than being a function of x, that function is a function of u, another variable, the derivative of this is equal to the derivative of that function of u, as if it was a derivative with respect to u. And then we multiply that by the derivative of u itself with respect to x. So what does this look like in practice? So we'll look at a simple example and then a slightly more complex example, but still relatively simple. So if we wanted to take the derivative of our function e to the x, well, we know how to do that. We covered that in the first review. That's simply e to the x. But what if we wanted to take the derivative of e to the minus 2x? So now our derivative, so our derivative is with respect to x, but what's in the exponent is not x. So what we're going to do is set that equal to u. So we're going to have u is equal to minus 2x. So now what we're trying to do is take the derivative with respect to x of our function that's a function of u. So the way that this looks is that we'll first take the derivative with respect to u. In this case, it's minus 2x. So we'll take the derivative with respect to minus 2x of our function, e to the minus 2x. And then we'll multiply that by the derivative, again, of u minus 2x with respect to x. And so this part right here is very similar to this over here. So we're taking the derivative of e to the x with respect to x. Here we're taking the derivative of e to the minus 2x with respect to minus 2x. So you shouldn't be surprised that that derivative is simply equal to e to the minus 2x. And then this part over here, the derivative of minus 2x with respect to x, of course, it's just a simple polynomial, and that equals minus 2. So our net answer is minus 2 e to the minus 2x. So you can see for this example here, we just had, we didn't really have another complex function. We just had a coefficient. And that coefficient just comes out when we take the derivative. But what if we did have a complex function in there? So, or not necessarily a complex function, but just, another function that wasn't 2x. So let's look at this example. So we'll take the derivative with respect to x of sine pi x squared. So if we were just taking the derivative of sine of x, we know from the last review that that's just cosine of x. But here, we're not taking the derivative of sine of x, right? We have another function inside of our sine function. So we can use the same principles of the chain rule that we've seen before. Here, in this case, our u is going to be equal to pi x squared. So we take the derivative with respect to pi x squared of sine pi x squared. And then we multiply that by the derivative of u, which is pi x squared, with respect to x. So just like we saw before, here we're taking the derivative of sine of something in the parentheses, but we're taking it with the derivative of the respect to what's in the parentheses. So that simply ends up being cosine pi x squared. And then to that, we'll multiply the derivative of pi x squared with respect to x. Again, just a simple polynomial. It ends up being 2 pi x. So our final answer here is 2 pi x cosine pi x squared. And so for these simple applications of the chain rule, what we're starting with is we're starting with a function we know how to take the derivative of, but then inside of that is another function we also know how to take the derivative of. So when you're doing the derivative of something like this, we can simply take the derivative of the outside, right, leaving the inside alone. So we take sine of pi x squared, and that gives us cosine of pi x squared. And then we multiply that by the derivative of the inside. And that's a simple way to think about the chain rule. So take the derivative of the outside function, leaving the inside alone, and then multiplying that by the derivative of the inside function. Another helpful rule for us is going to be the product rule. So this has an application like the chain rule. So the application for the product rule is simply going to be when we're taking the derivative of a function that is the product of two functions we know how to take the derivative of. So for example, if we're taking the derivative of two functions, so if we have a function that's f of x times g of x, uh, this is going to be equal to the first function, not taking the derivative of, and then multiplied by the derivative of the second function. And then to that we'll add the second function times the derivative of the first function. So again, just like the chain rule, we'll go through what this rule looks like in practice. So one example we'll look at here is if we're taking the derivative of x squared e to the minus 2x. So we know how to take the derivative of x squared. It's a polynomial. We know how to take the derivative of e to the minus 2x, but when you put them together, it becomes a more complicated scenario. But we can just use the product rule to evaluate this derivative. So we'll just follow the formula of the product rule. Here, x squared is our f of x, and e to the minus 2x is our g of x. So when we're plugging it into the formula, we have f of x, just x squared, and then multiplied by the derivative with respect to x of e to the minus 2x. And then we'll add e to the minus 2x times the derivative with respect to x of x squared. And when we do this, we'll note from the previous example that the derivative of e to the minus 2x is minus 2 e to the minus 2x. So that gives us minus 2x squared e to the minus 2x. And then the derivative of x squared, just a simple polynomial, is 2x. So it's this will add 2x e to the minus 2x. And that is the derivative of this function. And so we can use both the product rule and the chain rule to solve most any function. So if we have some crazy looking function, it's most likely going to be just the product of functions we know how to take the derivative of, or functions inside functions we know how to take the derivative of. And we can use any combination of the product and chain rule to figure out those derivatives. Integrals are not so easy. So we have a couple formulations for how to solve a few integrals that I went over in the first review. And if our integral doesn't fit into that form, we don't know how to take the derivative of it. So if we have something like this example here, x squared e to the minus 2x, we can't just use the product rule to take the integral of that function. We need to do something else. And we'll do that by using u substitution. So what u substitution does is it takes some function that doesn't fit one of the forms you know how to integrate and converts it into a form we know how to integrate. So for example, let's look at the integral of a function x e to the x squared dx. So this does not fit any form of anything we know how to integrate. So we have, a polynomial multiplied by an exponential, and that exponential is raised to x squared rather than just x. So it's not, doesn't look super easy going into it. But with this, we can do u substitution, and we're going to convert from a function of x into a function of u. And when we do that, we'll see that this function actually fits into a form that we know how to integrate. So what we'll do for this is we'll find out something that u is. So we'll set u here equal to x squared. And we'll do this for a couple of reasons. One, at the end, we'll see that this successfully converts it into a form we know how to integrate. But the idea behind this is just, well, we have this e to the x squared. I don't know how to integrate that, but I do know how to integrate e to the u. So maybe if we replace that x squared with u, we'll be able to get it into some form we can integrate. And so we'll do that, and then we'll take the derivative of u with respect to x. And if u is just x squared, this is equal to 2x, and we'll end up rearranging this to replace dx. And so what we'll see is that x dx is equal to du over 2. And I've written it in this way because if we look at this formula here, we have an x and a dx. So if we rewrite this integral, we can write it as e to the x squared times x dx. And now we've said that e to the x squared, well, x squared is u, and x dx is just du over 2. So we can rewrite this as e to the u times du over 2. And I'll rewrite that one final time as 1/2 times the integral of e to the u du. So e to the u du is something that we do know how to integrate, right? So just like u is just a variable, so e to the x, the integral of that is e to the x, so e to the u, the integral of that is e to the u. So it ends us up with 1/2 e to the u, and we can redo the substitution if we want, and end up with 1/2 e to the x squared as this integral. And if you don't believe me, you can take the derivative of 1/2 e to the x squared, and you'll come up with x times e to the x squared. And so now I will just mention integration by parts. This is something that it might come up on a homework problem, once over the course of the semester, but it's not going to be something that we focus on. So this is a way to solve integrals that don't simply fit into u substitution. And so one of these would be the example, the integral of x squared e to the x squared. You could do a simple u substitution and you'd find out that it doesn't quite work. We don't get into a formula that we know how to do. So the way that u substitution works is we fit it into a formula. We have the integral of some function u, some variable u, with respect to dv, where dv is something else. And this ends up equaling uv minus the integral of v du. And essentially what you do is you keep doing integration by parts until you end up with something that ends up being a successful u substitution where you can totally integrate it. So you might need to keep doing the same thing here with this v du and do another by parts integration for that. So what we'll end up doing for the most part over the course of physical chemistry is handling integrals that are much more complicated than any of the ones we've gone over here. However, these integrals will have pre-solved forms, most likely arrived at by doing multiple rounds of integration by parts. And we'll just look over those forms in the back of the book. So for example, this x squared e to the x squared is something that we'll see over the course of the semester. We don't know how to integrate it, but we'll just look up the answer in a solution, an integral table in the back of the book, and we'll be able to handle it that way. Because the point of the class is to go over look at some physical chemistry properties and arrive at interesting conclusions about physical chemistry. It's not necessarily can you do really hard calculus, but you will want to be able to do simple calculus and have that in the forefront of your mind as you're going through and solving problems and setting up problems, especially to be aware of these things. That's what the purpose of this review is. But this is not a calculus class. You want to have a good handle on basic calculus, the stuff that's in the review, but you don't need to go over it too much.